Swayam Prabha. Digital India. Educated India.
So, in the definition of curvature of a curve, okay, you would like the curvature to be the magnitude of the acceleration, okay, at least the scalar curvature, all right, and but then there can be different parametrizations of the curve, and different parametrizations of the curve will give different velocities. So, and therefore different speeds, okay, and therefore what we have to do is that first of all we need to normalize the speed. So we take unit speed curves. That of course means that the velocity vector never vanishes, and this is in particular it means that we have to take a regular curve, all right, for which there is a regular parametrization, for which the definition is the velocity vector never vanishes. Now the question is, if you take such a curve, you must also ensure it is unit speed. Only then you must measure its acceleration, which is the second rate of change, and take the magnitude of that and call that as the curvature. But the problem now is that if I take an arbitrary regular curve, what I have is that it is, I know its velocity vector is not zero at every point, that is the speed is never zero, but the speed could vary. I want a situation where the speed is 1, okay, so I want this unit speed thing. So what we did in the last class was to show that because of the arc length, okay, you can reparametrize the curve so that it becomes unit speed, okay, and so let me just go through this recipe again. So so you see the recipe to find the curvature of a curve is that you start with a curve with a regular parametrization gamma of t, okay, and regular means that gamma dot t never vanishes. Then what you do is you reparametrize it to unit speed. That means you have to substitute, you have to change the variable from t to u, okay, and when you do that, so you have to put this substitution, t is equal to g of u, so that your gamma t will become gamma of g of u, and this function of u, you call it as capital gamma of u, okay, and it turns out that this, what is this g of u, how is it related to the original parametrization? It's actually intrinsically related to the curve itself. G inverse, okay, so you see you have t is g of u, therefore g inverse of t is u, and u is the argument of gamma, all right, and the point is that g inverse t, which is just u, okay, this is the arc length function of t, okay, therefore the formula is, I mean the idea is very simple. You must have that gamma of s of t is equal to small gamma of t, okay, if you want to write it like this, okay. This is the relationship between the original regular parametrization and this capital gamma, which is the new unit speed parametrization, okay. And in fact I told you that this substitution that u is equal to so u is g inverse of t, which is just s of t, okay. This substitution you can change by a sign, okay, and that will not that will happen that will not affect the the curvature in any way, okay. See and why is that? That's because you see, once you have this, what you do is that you define the curvature is norm of, you take the you have to take the magnitude of the acceleration of the unit speed curve. So the unit speed curve is capital gamma u, okay, its velocity is d gamma u by du. That should be a unit vector because it's a unit speed curve. Then you again differentiate it, you will get d squared gamma u by du squared. That is an acceleration, you take its magnitude. So the curvature will be d squared gamma of u by du squared. This is the curvature, okay. And so therefore what I have to do is, essentially I have to compute this quantity and I will get the curvature. All right. But you see this, as I told you, you see this is a somewhat, difficult procedure to practically implement. So the simple example I gave you was just take the simplest example, namely the sine curve, which is the graph of the function y equal to sine x. Then you see the graph has coordinates x comma sine x, okay, and therefore this x is your parameter. Then what happens is that if you calculate gamma dot, okay, with respect to the parameter, you get 1 comma cos x, and this 1 comma cos x, because there is this 1, it's never going to vanish, so it's a regular parametrization, okay. This is true for the graph of any function. It will always be a regular parametrization, okay, because the independent variable will be the parameter, and when you differentiate with respect to that, you will get 1. So one component of the velocity is always 1, so it'll never vanish, so it will always be regular. Now what am I supposed to do? You see, I have to calculate d squared, so the curvature kappa is going to be d squared gamma by d squared gamma u by du squared. This is the definition, okay, where what is this u? This u is s of t. This is the u is your it is arc length function, okay. So I have to find out the arc length function, all right. But you see, if you think about it, the arc length function here will be, so you see d, so there is this relation that ds by dt, which is the speed, okay. This is the rate of change of arc length with respect to t. That is basically, it should be, the speed is the, it is this magnitude of the velocity. So this has to be equal to norm gamma dot. So basically ds is norm gamma dot dt, and if you want s, okay, you integrate from t naught to t ds by dt dt, and you replace this ds by dt by norm gamma dot t. Of course, in a differential way, you can write ds is equal to norm gamma dot t dt. You can write it like this in a differential way, all right. And you integrate it, then you get s, okay. And in the case of the graph of the sine curve, what it turns up is that you get you get root of 1 plus cos squared t, okay. And I was just trying to tell you that so this is the function t going to st. This is the arc length function, okay. And if you call that as u, your new parameterization is gamma of u, which is gamma of s of t. This is the unit speed. This is the unit speed parameterization, okay. But you see, you want a formula in terms of the original small gamma, because what is given to you is only the original small gamma, okay, which is in this case gamma of t is sin t comma sin t, because it's the graph of the sine curve, okay. From that I want the formula for capital gamma, okay. But the point is that if I know st, if I knew what capital gamma is, I can just plug st into it, and I will get, of course, this is only going to give you small gamma of t, all right. But the problem is that I don't know a priori this capital gamma. I need it. So the only way to do it is that I have to find out u. I mean, I'll have to find a way of inverting u and plug it in this gamma, small gamma, which I know. So if I want it in terms of small gamma, I have to write it. So write it as follows. So you see, gamma of u is gamma of s of t. This is small gamma of t, okay, where your u is s of t. But if you want to invert it, you will get s inverse u is equal to t. Therefore, if you write it like this, your gamma of u is also equal to small gamma of s inverse of u. Okay, if you replace t by s inverse u, because u is s of t. So you see, if I want an expression for gamma u, capital gamma u, you see, I have to find s inverse u, and then I have to plug it inside the small gamma, which I know already. But you see, what does it mean? That means, you see, this integral, the arc length integral, will give t going to st, okay. What is this? Basically, what you are doing is that this is your curve. Your parameterization already gives you a direction or orientation of the curve, which is how the point on the curve moves as the parameter increases, okay. So then what you are doing is you are taking a point p naught with which corresponds to t equal to t naught. So this is just gamma of T naught, okay? And at this point, the arc length is S naught, okay? And from this point, you are starting to measure the arc length. So you go some other distance along the curve. If you go along arc length S at point at T, so this P will be at T equal to T, and this point will be gamma T, okay? And if you want this arc length, okay, then it's given by this function. For every T, you have the distance from S T naught, a fixed point on the curve, to S of T. That is this function. So you see, this S is a function of T. Now what you have to do is you have to invert this. You have to call S of T as U, and you have to take the inverse function, which is this G should be, you know, S inverse of this should be S inverse of U. Okay. So the moral of the story is that you have to. So this is your T. Okay. So you have to invert it. Okay. And you see, already this integral is if you reduce it, it turns out to be an incomplete elliptic integral of the second kind. It's very, very hard to compute, and it is not expressible in terms of elementary functions. So this T going to S of T, this arc length function itself is not a easy function. Now imagine inverting it. That could be even more formidable. So this practically, you know, this method is not, if you try to use the method of the definition, you're going to get into trouble. Okay. But the point is that, you know, you can still prove formulas using that definition. You don't use that definition to make calculations like this, but you can develop the theory. Okay. So what we are going to do is we are going to show that, you know, with that definition, which is not so easy to implement, you can still show that you get the formula that we originally got. And the point is that the original formula did not assume unit speed. It was for any parametrization which is regular, and we will get back that formula which we got from geometry. Okay. So you should understand that is the power of math, that there is something highly theoretical. Okay. It may be even, if you're lucky, it's practically also, you know, implementable. If not, it will still have the advantage that you can get something out of it, and you can reconcile things that you can intuitively compute, like we intuitively computed the curvature using geometric ideas and taking limits. Now that you can confirm that is always true. Okay. So in fact, I was trying to also tell you what is this business about inverting an integral. Basically, you see, this is, if you write it like this, let us say T naught to T, okay, and then I will have to write HT on this side, and I have to put a HT naught here, okay. Then what happens is you are getting a function T going to HT, okay. Now, thankfully, this you know, inverting this integral is a very easy thing. It's just sine inverse of T. So H of T is sine inverse of T. If you invert it, it's very, very easy. If you call this as U, then, you know, sine inverse T is U. So T is sine U. Okay. So this is the inversion. So this integral is very easy. You are able to invert it. Okay. But there, this is sine inverse, for example, is an elementary function. So that's all right. But it's not necessary that everything is like that. Okay. So in fact, there are many integrals which are not expressible in terms of elementary functions. So you cannot write a nice closed form like this. Okay. So anyway, so the question is, what is the way out? The way out is that, you know, you have to undo this hitch in the definition, that to calculate the curvature, you have to use only a unit speed curve. So you see, given any parametrization gamma of T, calculating the arc length is very, very easy. The arc length is you just integrate norm gamma dot with respect to T. That will give you the arc length. But invert after, it's easy to write down. But computing that integral as a function, arc length as a function of T, that is not easy. That function may not be an elementary function. Further, you may not be able to invert it also. Okay. Therefore, moral of the story is that you need a formula. So we have to derive a formula for a general regular parametrization. Okay. And we want to obtain the original geometric formula that we got. So what was the original geometric formula? So let me write this out. Our originally we had gotten the formula curvature at the point T is norm of gamma dot cross gamma double dot divided by norm gamma dot the whole cube for a plane curve parametrized by gamma of t, of course regular, gamma dot t never 0. Okay, so we got this formula. The way we got this formula was a very geometric thing. What you did is you took at the given point you took the normal, at a nearby point you took the normal, you took the point of intersection, and then tried to find the limit as this nearby point comes to this point, and that point turned out to be the center of curvature. Okay, we proved that this can be done. Now the beautiful thing is that there it was only a plane curve parametrized by gamma. Okay, the fact is that this formula works even for a space curve. Okay, so this formula is correct even for a space curve, and how to get it is you can use this definition of curvature as being the magnitude, the scalar curvature as being the magnitude of a unit speed, of the acceleration of a unit speed curve, even though unit speed curve you cannot find, in practice. Okay, so you can use calculus to get this formula. So that's what we are going to do. But before that, I want to say something. There is also this other issue that when you make the definition of curvature, it should not depend on the parametrization. You see, this is another kind of issue. Okay, now we have more or less settled it. Okay, we have more or less proved that the curvature has got nothing to do with the parametrization, and I will explain how. You see, first of all, given a regular curve, what did we do? We showed that the parametrization has to be given by arc length. Okay, you can of course take arc length in with a plus or a minus sign. Okay, and that is essentially trying to measure the arc length in one direction or the other. Okay, but changing this sign will not change the second derivative. Therefore, you see the acceleration will not change. Okay, therefore you see this is one way of saying that the only choices you have for reparametrizing a regular curve so that it is unit speed is that you have to use the arc length or negative of the arc length. Okay, and then you see whether you use plus arc length or minus arc length, and then you can even add a constant. Okay, because it's a second derivative, you can actually when you do the first derivative, the constant will get wiped out. And essentially, you know what that constant is? It is the initial arc length measured at the initial point. See, basically, what is the so let me write this. We will show this holds even for space curves. Okay, we will show that. So you see, let me recall. So you have this gamma of t. This is regular. Then what you do is you write this as capital gamma of u. This is the unit speed parametrization. Okay, and what is the unit speed parametrization? This u is just s of t. Okay, and what is s of t? This is, if you want, integral t naught to t norm gamma dot of t dt plus s of t naught. Okay, because this fellow here is integral of ds. This thing inside is ds, and integral of that will be s from between the upper and lower limit. So you will get st minus st naught, and therefore you see I have to add this st naught here. So the moral of the story is that u can be this, and you can also take u to be minus of that. Okay, or u is equal to minus of s of t. Okay, and why does this minus sign come? That's because, you see, I told you that when you make this change of variable, you are making a change of variable like this. So let me remind you. Originally, your parametrization was going from an open interval a b on the real line to R2, which is, this was your gamma. This is t going to gamma t. Then what we did was we wanted a reparametrization by another variable u, where u goes to t, and we wrote g of u equal to t. All right, and this g inverse is exactly the arc length. Okay, and that was we got g inverse is the arc length s, assuming that g is monotonically increasing. Okay, if you had assumed g is monotonically decreasing, you would have got a negative sign. Okay, it's only because of this, the sign of g dash, or whether you're going to take g to be monotonically increasing or monotonically decreasing. Okay, it's only that changes the sign. But whether you put u is equal to st or u is equal to minus st, you see in both cases, you see that d squared gamma of u by d squared is unchanged. So the point is, whether you take u equal to st or u is equal to minus st, what will happen is this d squared gamma of u by du squared, that will never change. Okay, see, d squared gamma u by du squared is does not change. Does not change for these choices. Okay, that's because you see, when you do the first derivative, you will get a sign change. Then you do a second derivative, you will get one more sign change, and they'll cancel out. Okay, so the point is that whether you are going to use arc length or negative of the arc length. Okay, and that actually amounts to trying to measure arc length in one direction or the other from a fixed point. All right, so in any case, this is more or less, from this it's more or less clear that your definition of curvature, that has got nothing to do with parametrization. Okay, the only things that can happen is, the only reparametrization that you can have is arc length or negative of the arc length, and if you do that, the second derivative will not change. So this is one proof that the definition of curvature has got nothing to do with with your parametrization. Okay, depends only on arc length. Okay, look at it in another way. Look at the curve physically. See, if you take parametrization with respect to arc length, what you are doing is you are only trying to say that some point on the curve, you fix a point on the curve, you are saying some other point is gotten by traveling along this direction so far, that distance along the arc length. Okay, now you see, this has got nothing to do with any parametrization. So you see, the arc length is an intrinsic thing. If you take a curve, the idea of arc length is intrinsic. You take the same curve, give different parametrizations, the arc length, if you compute, you will get the same value, because arc length is something physical. Okay, it's the length of the curve along the arc that you're measuring. Okay, and what is really happening is that if you use two different parametrizations, you are just using two different, suppose you use gamma 1t and say some other gamma 2 of some w. Okay, in any case, what you are going to do, you are going to integrate norm gamma dot. Okay, and if you see what is that integration is, you are only breaking that curve into small polygonal segments. Okay, and you are adding them up, and then you are taking the limit when these polygonal segments become very small, which is exactly the definition of the Riemann integral. So this is what you are doing, you are taking limit of a sum, and that's a completely physical thing. When you are doing that Riemann integral, you are only calculating small pieces of polygonal arcs on the curve and adding the lengths. Okay, so that is completely physical and has got nothing to do with the parametrization. I want you to understand that. So moral of the story is, if you look at it from a physical point of view, if you take any curve, what is the most natural parametrization? It's obvious, it is the arc length. Take any curve like this, I take any point, call it as P0. Then at this point P0, you call the arc length at P0, you call it as 0. That is a reference point. You go in a certain direction. Then if you go to the point P, this P will be a function of S. That means this point will have xs, ys. It will have coordinates, and that will depend on this length s that you have traveled in this direction. As s changes, you will get various points. And now you see, this is completely physical on the curve. This has got nothing to do whether the curve is parametrized in one way or the other. So I want you to understand that this arc length parametrization is the most natural thing, and it has got nothing to do with any other parametrization. Okay, it's a more of a physical thing. Okay, so it doesn't change. And this is another way of justifying that. What you are now saying is, take what is the curvature of a curve, you just take the natural arc length parametrization, okay, and take the second derivative and take the magnitude of that. That's your curvature. Okay, and what is the advantage? when you take the first derivative, it is automatically a unit vector because your function, what you are measuring is the rate at which s changes with respect to s. Okay, you're measuring the rate at which the s vector changes with respect to s. Okay, and that has to be the magnitude of that has to be always 1. Okay, all right. When you measure gamma dot, what is gamma dot for a parametrization gamma of t? It is d gamma t by dt. You are measuring rate of change of gamma of t with respect to t. But in this case, you are measuring capital gamma of s change with respect to s itself. Okay, and that has to be the way capital gamma s changes is exactly the way s changes. So you see that the magnitude must be 1. Okay, that's why you get unit speed when you take the natural parametrization by arc length. And then if you take the second derivative, you get the curvature. That's all. So it's physically very, very clear that this definition of curvature has got nothing to do with any parametrization. Okay, so no matter what parametrization you use, you will get the correct answer. There's only one hitch, that you might measure arc length in the other direction, because there are 2 ways you can traverse the curve. In that case, it amounts to just changing s to by a minus sign and adding a constant. Okay, then anyway the second derivative will again not change. So you see, this is another way to see that this curvature definition is correct. Okay, it has got nothing to do with any parametrization. So what we'll do is, with this certitude, we will derive the curvature formula, okay, for a general space curve, and show that it agrees with the geometric formula that we already got. Okay, so how do we do that? So here is so I have to do the following thing. Start with gamma of t, regular parametrization. Okay, then have unit speed parametrization given by capital gamma of u is equal to small gamma of t, where u is s of t. Okay, and we will assume I will take u is equal to plus s of t, which means that I am measuring with respect to some point on the curve, and I am measuring in terms of increasing arc length. If you had put minus, it means that you are measuring it in the other direction. Okay, and mind you, there is a direction to the curve. Whenever you give a parametrization to the curve, it's said to be oriented, namely the direction on the curve is the point, the direction a point on the curve moves as the parameter increases. So what we are assuming is that we are assuming that the curve is parameterized by increasing arc length, and because it's an increasing function, you put plus s and not minus s. Okay, so this is the situation. And what do you have to find? You want the curvature at the point t, which is supposed to be what? It is d squared gamma of u by d u squared. And of course I want the norm of that. I want the magnitude of that. So this is the definition of the curvature. This will be a unit speed curve, and you take its magnitude. That is the curvature at that point. And what we want to arrive at is that this is equal to this formula, gamma dot cross gamma double dot by norm gamma dot the whole cube. Okay, and this formula is useful because you are already having this small gamma. So you see, this is easy to compute. Notice that capital gamma is not easy to compute, and therefore this is also not easy to compute. But we are proving this is the same as that. So you only theoretically need the existence of a unit speed parametrization, but you never use it. You only use it to prove this formula. Thereafter, you forget the unit speed parametrization, always use the formula whenever you want to make a calculation. Okay, and you can use any regular parametrization, small gamma of t. Okay, so first of all, you can verify certain things. Why is this capital gamma u unit speed? Okay, so you calculate if you calculate gamma dot u. Okay, so this is what? This is d gamma of u by du. Remember, this dot is always first derivative with respect to the argument. So when I write gamma of u, the argument is u, the variable is u, and when you write gamma dot, it is d by du. Okay, whereas when I write small gamma dot of t, then the dot there is d by dt. So you have to be careful about that. So you see, you take this. Now, use this thing here. This is the same as writing d by du of small gamma of t, okay? But the substitution is u equal to s of t. This is what you're doing, all right? And if you write it like this is what are you going to get? You're going to get, see, I can write this by chain rule as d, and of course, mind you, this side is a function of u. So this is also a function of u. So this also must be a function of u. So I have to be careful. I have to write at t equal to s inverse of u. Okay. Only then it will finally give you something that depends on you. Okay. And now what I am going to do is I am going to use this, and then I am going to use the chain rule. So this d by du can be written as d by dt of gamma t into dt by du, and again I put at t equal to s inverse of u. This is just chain rule. All right. But what is dt by du? You can see this, that you see u is s of t, okay, and du by dt is the same as ds of t by dt, okay, and ds of t by dt is what? This is just norm gamma dot, okay, because ds is norm gamma dot dt, okay. Therefore, you see that this quantity is d by dt. Of course, d by dt of gamma t I can write as gamma dot t. So let me write that. So this will be gamma dot of t times this dt by du. I can mind you, dt by du is also 1 by du by dt, okay. And the reason is, don't think that dt by du is actually quantity dt divided by quantity du, okay. It's not like that, of course. It is an operator. And when I say dt by du is 1 by du by dt, this is actually the chain rule applied to the fact that u and t can be inverted, okay. So the moral of the story is I'll get gamma dot t by norm gamma dot let me be careful and write, oops. So let me be careful and write norm gamma dot, let me put an extra t there initially so that it's clearer, at t equal to s inverse of u. That is what it is, okay. And so this is your gamma dot of u, okay. Now is it clear that gamma dot u has norm 1? Because look at the norm of this. Norm of gamma dot by norm gamma dot is 1. So it's very clear that this is indeed a unit speed parametrization. Clearly, norm gamma dot of u is equal to 1. This is clear, okay. So when you make this parametrization, you are getting, of course, you are getting unit speed, okay. So that is there anyway. You could have started with this formula directly. That's correct. But that is right. So what you're trying to say is that, it's clear that gamma dot is not unity. If gamma dot is not what I mean is, if gamma dot is not a unit vector, then you can get a unit vector by dividing it by its norm. So you could have taken gamma dot by norm gamma dot, and that gives you a unit vector, okay. But you will have to do some work to show that, this is a reparametrization of the original gamma. Because I mean, you see, this gives you a hint as to what has to be done, but the point is that you will have to show that this is a valid parametrization. Essentially, that's what we have done. Essentially, what we have done is we have done that. The obvious way to think about it is that if you give me any regular parametrization gamma, then gamma dot need not be 1. But if I want to make gamma dot to be a unit vector, all I have to do is take gamma dot and divide by norm gamma dot. Dividing by norm gamma dot will entail that, I need regularity. I need that the gamma dot never vanishes. But if I do that, then this gives you the unit speed parametrization, okay. And it is obtained from the original parametrization by a change of variable, differentiable invertible change of variable. That is what needs to be proved. I mean, that's what we have done so far. So it is the intuition is correct, that you just take gamma dot and divide by norm gamma dot. That should be the unit speed parametrization, okay. But there is some intervening theory there that needs to be filled in, okay, which is what we did. All right. So So anyway, we have got this speed as 1. Now our aim is you have to calculate this, you have to calculate the curvature, which is the second derivative. All right. So what I need to do is I need curvature at t, okay, which is the same as curvature at S inverse of u if you want. Okay. This is to be you have to calculate gamma double dot of u, capital gamma double dot of u, and then you have to take its norm. So I think I have put the norm here. Yes. So I have to calculate this. Okay. And how do you calculate this? Of course, the way to do this is that when you want to calculate a norm of a vector, you just take the vector, take dot of it, you'll get norm square and take square root. So the most obvious thing is you will take positive square root of gamma double dot u dot of gamma double dot of u. This is what you'll do. Okay. So in particular, but the point is that at the end of all this, I want everything only in terms of small gamma and t. I don't want any u there. Okay, I don't want any u, I don't want any arc length, I don't want anything there. See, all these things should go away. Finally, my formula should just depend on small gamma t, which is the regular parametrization that I started with, which need not be unit speed. Okay, that is what is helpful for calculations. So you have to do this. So you see, how do you? So let us calculate. See, already we have a formula for gamma dot u. So let me write out. So gamma dot of u is small gamma dot of t by norm gamma dot of t. Okay, at t equal to S inverse u. Okay, and now you calculate gamma double dot of u. Gamma double dot of u is you have to apply d by du to this guy. Okay, and again use the chain rule, writing it as apply d by dt to that, and then put dt by du. So this will become d by dt of this, okay, into dt by du, and again use the fact that dt by du is 1 by du by dt, and this is 1 by ds of t by dt, and this is 1 by norm gamma dot. Okay, so norm gamma dot of so let me write norm gamma dot of t. So the moral of the story is that you will get, so I have to apply d by dt to this expression here. Okay, essentially this expression I have to use quotient rule. So what I will get is, you see, denominator norm gamma dot of t squared, norm gamma dot of t, and then I have to differentiate gamma dot t. Mind you, what you are doing is, when you are differentiating this quantity here, the numerator is a vector, the denominator is a scalar. So what you are differentiating is a scalar variable multiplied by a vector variable. All right, and so it's not one vector divided by another vector. That doesn't make sense. Okay, because there's a scalar in the denominator, your quotient rule still works, because it's actually another avatar of just the product rule. Okay, the product rule still applies to a scalar function multiplied by a vector function. Okay, and you can think of this as gamma dot, the vector function, multiplied by the scalar function 1 by norm gamma dot, and it's actually product rule for that. Okay, so watch out that all the expressions we are writing are all vectors. Okay, there are no whatever you are dividing by are all scalars. You have to remember that. So you see, you have norm gamma dot, and this, the numerator, I will get d by dt of gamma dot, I will get gamma double dot of t. Okay, minus, then I will get numerator constant derivative of the denominator. Okay, I'll get this, and then outside there is this guy, which is going to give me a 1 by norm gamma dot of t. Okay, so the moral of the story is that I will get norm gamma dot of t cube. Okay, and here I am going to get this term. So let me write it. So be careful with the dots. Don't put a dot too many. Gamma dot of t norm. This is a gamma double dot of t minus gamma dot of t, t by dt of norm gamma dot of t. So I need to tell you, it's obvious how to calculate d by dt of norm gamma dot of t. Okay, from the idea, I mean, you can do it in two ways. Basically, the idea is you use the definition of norm as coming out from a dot product. So you see, one way you can do it is, you see, d by dt of norm gamma dot of t is by definition d by dt of square root of, if you want, gamma dot of t dot gamma dot of t, okay, and derivative of a square root is 1 by 2 square root of gamma dot of t dot gamma dot of t, okay, and into d by dt of this product gamma dot of t dot gamma dot of t, okay, and this is going to be, if you apply the product rule, I'll get 2 gamma dot dot gamma double dot. So basically I get 2 gamma dot dot gamma double dot divided by 2, and the denominator is of course norm gamma dot, okay. So basically at the end I will get gamma dot dot gamma double dot divided by norm gamma dot. This is what I get. That is this expression. The other way is, you can also directly write, the other way of looking at it is, you can directly write it like this. You know that norm gamma dot of norm gamma dot squared is gamma dot dot gamma dot. You simply apply d by dt, you will get 2 norm gamma dot into gamma into d by dt into d by dt d by dt of norm gamma dot is equal to, if you do d by dt on the right side, you will get 2 gamma dot dot gamma double dot. This 2 cancels, and again you will get the same expression. You will get d by dt of norm gamma dot is gamma dot dot gamma double dot divided by norm gamma dot, which is what we have got here. Okay. So there are 2 ways of getting this, but they are essentially the same. In one you are differentiating the square root, the other you are not, okay, but you will anyway get the same thing, okay. So whichever way you do it, so we can replace this term here. So what you get, so let me write it here, it's kappa t here, the curvature. So kappa t is therefore equal to norm gamma dot of t into gamma double dot of t minus gamma dot of t into this term here is this term, which is gamma dot dot gamma double dot divided by norm gamma dot and the whole divided by norm gamma dot cube. So I am going to just suppress gamma of t. I am going to suppress the t in gamma t, gamma dot, gamma double dot, and all that. And always remember that the dot is with respect to the t, and t is the variable for the small gamma. Okay. For the capital gamma, which was the unit speed parametrization, the dot represents d by du, and u is the variable, and u is nothing but the arc length s of t. Okay. So this is going to be, let me write it, is norm gamma dot gamma double dot minus gamma dot into gamma dot dot gamma double dot, and if I take LCM, I will get a norm gamma dot squared here in the first term, and then here I will get norm gamma dot to the power of 4. Okay, I will get this. Okay, and now you see this numerator is, what is this? This is just going to be so I wanted to say wait. So I have to be careful. So there's something that I have messed up. Yeah, I still have something to do before I can write kappa of t. You see, I have to compute norm of this. Okay, so I wrote this kappa t here a little too soon. So let me remove this. So you have to be careful, because I shouldn't write that, because the expression on the right is a vector. Okay, and I'm trying to in a hurry write kappa t, which is a scalar. Okay, so there is something that I've done which is stupid. So let me write it here. So what was on the left side was this capital gamma. Oops. Yeah. So let me write the left side correctly. So it was gamma double dot of u is this expression. This expression. So let me write it here. Gamma double dot of u is this. Okay. And mind you, this is a vector. So you see, look at the thing. This is a vector. This is scalar. Okay. And similarly, this is a vector. This is a scalar because it's a dot product. And the denominator, you have only a scalar. So the net effect is a vector. Okay. And that is just gamma double dot of u. And the how do you reconcile with the u? There is always this at t equal to s inverse u. Okay. This is always sticking around all the time. Okay. So if you remember, there is this t is equal to s inverse u there. Okay. So that both sides are functions of u. All right. Now what do I have to do? The curvature is, you have to dot this with itself and write the formula. So So let's do that. Let me rewrite this. The curvature at T, which is the curvature at S inverse of U. Essentially, you are going to use that. Yeah. So you can, as you can guess, you are going to use vector product of 3 vectors. Okay, and then you are going to use a little bit of geometric interpretation. Okay, so you see, so it is a good observation that the numerator is there is a vector triple product in the numerator. Okay, which has to be used. Okay, so to get kappa, what I need to do is that I need to take the dot product of this with itself. Okay, and then I have to take positive square root. Okay, so gamma double dot u is the acceleration of the unit speed reparametrization, and its magnitude is its the length, which is you take dot with itself and take square root. Okay, now I have to do that for this thing. All right, and there I mean, you can do it either way you want it, either by thinking of the cross product or without that, and you will see that at the end you will end up with the right formula. So one way of doing this is so if you just write it out as a full blown account, what you will get is, I'll have to take norm gamma dot squared gamma double dot minus gamma dot double dot. So divided by norm gamma dot to the 4. I have to dot it with this, the same thing, which is you have to be careful writing these dots. Minus this is only one dot. And I have to take square root of this. You see, I have to take dot of this with itself. Okay, and perhaps it's as you would think, it's easier to just expand this and look at it as a cross product of 3 vectors. So you will get gamma. So look at this term, gamma dot squared gamma double dot minus gamma dot times gamma dot gamma double dot. Okay, and so what is this? And note that norm gamma dot squared is again gamma dot gamma dot. So you will get gamma dot gamma dot into gamma double dot minus gamma dot into gamma dot gamma double dot. Okay, this is this is actually A cross B cross C. Okay, and the formula for this A, what is this? A dot C into B minus A dot B into C. Okay, so if you basically if you look at this so if you look at this formula, you have to put your A. So your A is gamma dot. Okay, everywhere. Okay, and your B is gamma double dot. That is here. Okay, and your C is again gamma dot, and that is correct. Okay, so if you make this comparison, then you will see that you will get gamma dot cross B is gamma double dot cross C is again gamma dot. Okay, and therefore this term is just, if you take dot on the numerator, you will get simply norm squared of that. Okay, and there is a square root. So essentially what you will get is that K of T is, if you want, K of S inverse of U is actually going to be the numerator. I am going to get just norm of gamma dot cross gamma double dot cross gamma dot. Okay, divided by in the denominator I have a norm gamma dot to the 4. All right, and so there are so now you see, just think about it, this gamma dot cross gamma double dot, the direction of that the cross product is perpendicular to both of the original vectors. So you see this gamma dot and this vector, they are perpendicular, and therefore when you take the cross product, then by the definition of the cross product of two vectors, it is the modulus of the one, the modulus of the multiplied by the modulus of the other into the sine of the angle between them, which will now be 90 degrees. Okay, so in this case it will just be the product of the moduli. So this is just going to be norm gamma dot times norm gamma dot cross gamma double dot divided by norm gamma dot to the 4, and then one of this will cancel and you get your formula gamma dot. Okay, so so you see we have finally arrived at the formula that we wanted. Okay. And what you must appreciate is that, see, in arriving at this formula you have used the unit speed parametrization. Okay, it has because originally you computed this expression only as the second it is a second rate of change of the unit speed reparametrization. It's capital gamma double dot of u. Okay, that's where it is used. All right, afterwards you are able to get the formula that you want. So finally you have this formula for gamma t, any regular parametrization, not necessarily unit speed. Okay, the curvature kappa t is given by this nice formula. Okay, now you see that advantage of this formula, you can easily compute the curvature of the sine, the graph of the sine curve. Okay, easily can get the curvature of the graph of the sine curve. Gamma of x is equal to x comma sine x. Okay, so with this you can easily do it, but it's as I explained to you, it's impossible to do it with the definition that you take a unit speed reparametrization and then take the second rate of change and then take its magnitude. Okay, so you see this is very direct. So as a particular example, let me give you compute the curvature of a helix. Okay, so it's a very simple example. So the situation is like this. You have this. So this is your x plane, this is your y plane. I mean, this is your xy plane, and then this is, let's say, this is the z. Oops. This is the z. Okay, and there is a base circle of radius, let us say a. Okay, and your helix is winding like this. Okay, and the parametric equation of the helix is given by if you want a cos theta, so a cos theta, a sin theta, b theta. Okay, where theta is a real variable. All right, and what you can understand is that the helix is contained, the points of the helix are touching the cylinder whose base on the xy plane is a circle of radius a. Okay, that, and then this b has got to do how much the helix moves up in one turn, which is called the pitch of the helix, and you see one turn corresponds to theta going by 2 pi. So the z coordinate will change by 2 pi b. So you see this 2 pi b. So I am assuming a positive, b greater than or equal to 0. Of course, if I put b equal to 0, you can imagine I am going to get a plane curve which is nothing but a circle. Okay, and if b is positive, then you get a helix. Okay, and 2 pi b is called the pitch of the helix, and this is actually this distance. Okay, if you think of it as a screw, then this is the pitch of the screw actually. Okay, so what is the now this is a parametrization in the single variable theta. Okay, and now you can calculate the curvature. So you have gamma of theta is this, sorry, a cos theta, a sin theta, p theta, gamma dot of theta Now you see dot means d by d theta, okay. So I'm going to get a squared here, and I'm going to get another a squared here, and I hope the sign is correct. Yeah, so plus I'll get plus k cap into I'll get a squared. Okay, so basically, so norm. So let me write this out. Therefore, norm gamma dot cross gamma double dot is going to be this thing, AB sine theta into I hat minus AB cos theta into J hat plus A squared into K hat, and then and norm of that, and that will give me square root of some of the squares of the components. So A squared B squared sine squared theta plus A squared B squared cos squared theta plus A squared, and this is going to be A squared, something's wrong. Yeah, here there should be a square, yeah. So this is going to be A squared B squared plus A power 4, and I'm going to get finally what? An A will come, and inside I'll get root of A squared plus B squared. Okay, that's so I get this. Okay, then what do I have to calculate? The curvature at theta, because theta is a variable, is norm of gamma dot cross gamma double dot by norm gamma dot cube. What is norm gamma dot? So here from here you see norm gamma dot is square root of A squared sin square theta plus A squared cos squared theta plus B squared. So it's going to be simply A squared plus B squared, and that's it, right? So therefore I'll get A into root of A squared plus B squared by root of A squared plus B squared the whole cube, and then therefore I'll get A by simply A squared plus B squared. That is the curvature. Okay, and when the case when this helix is a circle is when B is 0, and in that case you get A by A squared, which is 1 by A. Because it's just a circle of radius A, the curvature is 1 by A, it agrees. Okay, so this is what you see here is that the helix has constant curvature. Okay, and not only that, it's not a plane curve, it has also torsion. Okay, and we will see later on that if you think about it, it's steadily climbing. Okay, and this steadily moving out of the plane of curvature. Okay, that thing is measured by the torsion, and we will see later on the torsion is also constant. Okay, so the moral will be that helices will be the curves for which curvature and torsion are constant, and then the converse is also true. If you take a curve whose curvature and torsion are constant, it has to be a helix. Okay, so you can prove that. So this is a demonstration of this formula, how easily it can be used. And what you must appreciate is, you see, the motivation for this formula comes from geometry. Okay, the geometrical derivation which involved just a plane curve and using simple calculus. But at the end you are able to do it in general. Okay, so that finishes our getting at good formula, good definition of curvature, and getting a good formula for curvature which works for any regular parametrization. All right, what I need to next go into is I need to get into torsion. Okay, then I also need to get into these issues such as trying to show that for example, plane curves are controlled only by the curvature, the sine curvature, and the space curves are controlled by the curvature and the torsion. That means for plane curves only the curvature is enough to classify, the sine curvature is enough to classify. Okay, up to isomorphism. Okay, we have to make sense of what isomorphism means. All right, it will be actually rigid motions, and similarly the space curves will be completely classified by curvature and torsion up to isomorphism. There again the isomorphism will mean rigid motion, and this idea of rigid motion has to be made concrete by using orthogonal transformations. Okay, so that is what we will do next. Okay, so I will stop here.